For Unit 9 on ozone and ozone depletion. I want to remind you that just because it's not mentioned in here doesn't mean it won't be on the exam. There's a ton of other resources that I've posted for you, notes, PowerPoints, and of course class lecture that has been recorded. So this should just kind of briefly remind you of what the most important things were from this unit. And I'm going to start with ozone. I'll do another review on climate and then climate change, and then one later on about biodiversity loss as it pertains to endangered and invasive species. So first, ozone. Ozone is 3 molecules of oxygen that are covalently bonded together. That means that they share electrons, so they basically function as one thing. Ozone is found in 2 places in the atmosphere, and depending on where it's found, it has really different purposes. So when we talk about ozone today, we're going to be talking about ozone in the troposphere. Ozone in the stratosphere, Ozone in the troposphere is a pollutant, and we talked about it in the air pollution unit in Unit 7. So in the troposphere, which is the layer directly on top of Earth, it is a pollutant, and that's not what we're talking about today. Today we're talking about stratospheric ozone. And ozone in the stratosphere, if you remember, the stratosphere is the layer above the troposphere. It forms this layer and it protects us from UV radiation. UV radiation is a harmful radiation that can cause skin cancer and disrupt ecosystems. So ozone being there protects our Earth from harmful UV radiation. And how it works is that UV radiation, instead of being able to penetrate the ozone layer breaks it up. So what happens is here we can see these are the 3 different types of oxygen molecules that we'll have in our atmosphere. We have atomic oxygen, which is just 1 molecule of oxygen. Diatomic oxygen, this is O2. This is the form that we breathe, oxygen gas. And then ozone, which is O3. So how it works for protecting us is that UV radiation, instead of coming through and striking Earth, it ends up striking this molecule of ozone, causing it to break into atomic oxygen and diatomic oxygen. So we receive that energy. That energy is received by our ozone molecule and then causing that ozone molecule to break up. That UV radiation isn't going to come to the Earth because it's already been used up by performing this reaction. And now ozone, this diatomic oxygen and the atomic oxygen are reactive, so they just form back together again and recreate ozone. So as long as there are free oxygen, free diatomic and atomic oxygen in the atmosphere, they will form ozone. That ozone will receive that UV radiation, break apart, and then join back together. So this molecule works very well at receiving that UV radiation, absorbing it so it doesn't strike Earth's surface. However, as we saw in the mid-century, mid-1900s, is that there are things that we can do to deplete our ozone. So the biggest thing that we've done is we have these, I call them CFCs, chlorofluorocarbons. I'm going to keep calling them CFCs because that's a mouthful. They're found in refrigerants and coolants. CFCs we'll talk about next chapter, but they're a greenhouse gas. What we're going to talk about today and why they're important today is because they're atmospheric depleters. So what CFCs do is they insert themselves into that reaction that I just showed. So naturally UV radiation hits that ozone, it separates, and then naturally it forms back together, and that reaction can happen over and over again. And so that UV keeps being absorbed by ozone. But what happens is if there's CFCs that have been released and they're in the stratosphere, that UV light is going to hit the CFCs as well. And when the UV light hits the CFCs, one of those chlorines is going to pop off of the CFC, and then it's going to bind to that ozone molecule, and it breaks it apart so that you don't have ozone. And now that free oxygen molecule, that monoxide, that atomic oxygen molecule is bound to a chlorine, it can't bind back to the diatomic oxygen because it's bound to the chlorine. So it ends up breaking apart that reaction, breaking apart that molecule, that ozone molecule, and then the ozone molecule can't reform. So we end up with that UV radiation is able to penetrate into the Earth's surface instead of being stopped by ozone, because that ozone's been depleted by CFCs. So in the 1980s, they realized there was an issue and there was a growing ozone hole around South Pole. And so what we started doing is replacing these ozone depleting substances. We started replacing CFCs with hydrofluorocarbons. So there wasn't that chlorine anymore. Instead, there's a hydrogen. And so that's great because now there's no more chlorine in the ozone to stop that atmospheric ozone from reforming. The issue is that HFCs are a greenhouse gas. Now, CFCs are a greenhouse gas as well. So it's the same there. However, we don't have this issue with ozone depletion with HFCs. So the Montreal Protocol is what started the substitution of HFCs for CFCs. And it worked. Within 50 years, we've seen the chlorines have almost disappeared entirely. The hole around Antarctica has really started to close up. And the Montreal Protocol was enacted in 1987, and since then we've seen a lot of gains in terms of ozone depletion. We don't really have, so it's not an issue anymore. Now, I want you to see here in 2065, this there around Antarctica, around the South Pole, the ozone still is thinner there, and that's natural. There are natural factors that deplete stratospheric ozone. So chlorine is found naturally in the atmosphere. And what happens is during the Antarctic winter, the stratosphere fills up with clouds that are full of ice crystals. And those ice crystals melt in the spring, and sometimes those ice crystals have chlorine in them. And so when those ice crystals start to melt, they convert less chlorine into more reactive chlorine, and then that chlorine interacts with the ozone the same way that the chemically created, the man-made created CFCs and chlorine do. But we end up seeing the thinning of the ozone during the Antarctic spring, and then it is able to kind of restore itself. So it's a little more cyclical. And that's it for ozone.